Okay, so here's where we were last time. We were talking about Jordan canonical form. Jordan canonical form takes a while to talk about. In fact, it takes a while just to define what the form even is. It's just a complicated structure. So let me remind you what we talked about last time. First of all, context. Where does this even come up? It's part of this program that we have of trying to diagonalize matrices. Big applications of which are coming later in Chapter 6. Sadly, you cannot always diagonalize matrices. Big result we saw last time, I think it was, that you need a basis for Rn exclusively made up of eigenvectors. And sometimes you just don't have enough eigenvectors. They just aren't there. And so it's not possible to find that basis, and therefore the matrix is not diagonalizable. The consolation prize, when you cannot diagonalize, you can always put a matrix into Jordan canonical form. So it's not as nice as a diagonal form. Diagonals are great. But it's always possible. Every time, no exceptions. So that's where we're at. The form itself, remember, has kind of different levels of structure. At the top level is what I like to call the eigenvalue block structure. So there are these blocks on the diagonal in the sense that their appropriate corners are exactly on the diagonal. There are these blocks called that I like to call eigenvalue blocks, and they are closely related to the eigenvalues. Specifically, let me just pick one. Let's look at this eigenvalue block. All of the diagonal entries are the corresponding eigenvalue. And the size is the multiplicity of that eigenvalue. So this thing that I call the eigenvalue block is, as you can see here, very closely connected to the eigenvalues, and that's why I think this is a reasonable thing to call it. Okay, other things to know about the eigenvalue blocks. The big one is everything outside of the eigenvalue blocks, all zeros. That's great news. Let me just remind you, we like zeros. Zeros represent things you don't have to worry about. Right? Okay, so that's good news. Okay, what we're going to do now is turn up the magnification on our little microscope inside of this eigenvalue block. What's inside of that eigenvalue block? Here it is. Here's that eigenvalue block. Zoom in a little bit. Inside of that eigenvalue block are more little blocks. Also on the diagonal, in the sense that their appropriate corners are literally exactly on the diagonal. These little blocks inside of the eigenvalue blocks are called basic Jordan blocks. Sometimes it's called Jordan blocks. Okay. Again, all zeros outside of the block. So we already knew that there was all zeros out here. Outside of the eigenvalue blocks, we knew that was all zeros. Now I'm saying even inside of the eigenvalue blocks, as long as you're outside of the basic Jordan blocks, all zeros. So what we have here, you can see already this Jordan canonical form it's pretty tight. It's pretty closely diagonal. It's almost diagonal in the sense that as we get closer and closer to the diagonal, we keep getting more and more zeros. Okay, lastly, what's inside of the basic Jordan blocks? Here's the answer. They're all basic Jordan blocks look the same. Let me get my colors straight. All basic Jordan blocks look the same. They all have this structure here. Don't forget, of course, we already know what's on the diagonal. Right? The eigenvalue is on the diagonal of the entire eigenvalue block, so and therefore, of course, is on the diagonal of the basic Jordan blocks. And the only other non-zero entries are these ones just above the diagonal. That's it. Again, with the zeros, everything outside of the diagonal and just above the diagonal, all zeros. Okay, so that's the rules. It's a weird set of rules, but that's what defines Jordan canonical form. And so you might ask, what an odd little structure. Why would we write down such an odd thing? Well, the answer is twofold. First of all, this is something we can always achieve. Right? Almost there. You can always put a matrix into this form. Right? And the fact that you can always do it makes it, there's something kind of nice about that. If you can figure out how to understand Jordan form, then you can understand, well, any matrix in some sense. Any square matrices only, of course. But this is something that's always achievable, and that's really nice. The other thing that's really nice about Jordan form is not only is it always achievable, but again, look at all the zeros. This is almost diagonal. It's really close to diagonal. And since it is a consolation prize in our attempt to make an actually diagonal matrix, being almost diagonal is nice. Again, lots of zeros. Zeros make things convenient. Okay. Alrighty. So those are the rules. Let's see some examples. Here's some matrices that are in Jordan canonical form. Let me walk through that structure with you. Here is a eigenvalue block and another eigenvalue block, inside of which you can see basic Jordan blocks. That's a basic Jordan block. Notice eigenvalue on the identity. On the diagonal. Only ones above the diagonal fits the required form. Now, inside of this other basic, in this other eigenvalue block, that and that are basic Jordan blocks, and this is somehow a little unsatisfying. Wait a minute, where are the ones? It's going to seem a little weird, but let's look at this very, very bottom, 1 by 1 basic Jordan block I claim. There is only one entry. That entry is diagonal. Vacuously, all of the diagonal entries are 1. There are no off the diagonal entries to consider. Right? So this, in a very sort of default kind of fundamental way, is actually in the form of a basic Jordan block. So, all right. So that's the structure there. Do be careful. Don't make the mistake. Common mistake. A lot of students will say, let's make this. Let's call that a basic Jordan block. I point out you can't call that a basic Jordan block, because if this were a basic Jordan block, now very nicely you do see eigenvalues there on the diagonal, but above the diagonal you do not have all ones. There is one in this, in this candidate hopeful would-be basic Jordan block. There is an entry just above the diagonal. It would be required to be 1, but it isn't. So that is not a basic Jordan block like that. So again, you have to do it. Like we did before. That and that. Everybody on board? Questions? Yes.
You can't overlap blocks, right?
Correct.
So, okay.
Yes, a good point. You cannot overlap the blocks. The blocks are they have to sort of go right next to each other, but not overlap. Great question. Anybody else? Okay. All right, here's another one. Okay. Eigenvalue block. Eigenvalue block. Now let's see here. Can we do this? Can we call that a basic Jordan block? No, we can't, because there would be the above the diagonal, and that entry there would need to be a 1, but it isn't, so that's not okay. You cannot call that a basic Jordan block. What about this? Here, let me get rid of that. What about this? Can I call that a basic Jordan block? Nope. Again, That would need to be a 1. Furthermore, how else would you finish this? Are you going to make that a basic Jordan block? And then if so, look at that. That would need to be a 0. That's outside of the basic Jordan blocks. Has to be a 0, but isn't. All right, so that doesn't work either. Not hard to persuade yourself. There's only one way to do this. And that is like so. Yeah. That satisfies all the rules. Then down here in this other eigenvalue block, again, only one way to do it, like that. Notice 1 just above the diagonals. All zeros outside of the eigenvalue, let me do this in red, all zeros outside of the eigenvalue blocks. All zeros outside of the basic Jordan blocks. And then also 0 everywhere except for the diagonal and off the diagonal. There and there. Okay. Okay, lastly, just another example. Eigenvalue block. Eigenvalue block. Basic Jordan blocks have to be like this. And like this. Only one way to make it fit. Everybody see how this works? Any questions? Okay. Right. Okay, so reminder, let's go back to where we started here. What we're doing here is this is, part of our process of trying to diagonalize. We're considering what if you can't. So it remains, though, that we were trying to diagonalize. So we were talking about change of basis. Right? We're going to say instead of looking at the basis we started with, we want to do a different basis. We're not changing the underlying linear transformation. We just want to think about it from a different point of view, in a different language, if you like that metaphor. Change of basis for linear transformations is by similarity, conjugation. Right? So when we say that you can always put a matrix into Jordan form, what we're saying is give me any matrix given an appropriate change of basis, the result would be in Jordan form. And so, let's just write that down. I mean, here's what change of basis looks like. Here's that conjugation, aka similarity. And again, it depends on which way you're going. Right. Specifically, the way you do a change of basis on linear transformations is to conjugate with a change of basis matrix. So this matrix here, this P matrix, is a change of basis matrix. One of these I things with different bases. Here we're converting from B to S. Don't forget these change of basis matrices have a nice feature, and that is whatever the input basis is, that's telling you what the columns are in the matrix. Of course, don't forget that when I say the input basis are the columns, what I mean is the input basis vectors with respect to the output basis. S in this case, which is standard basis, so that's not. But always with respect to the output basis. But punchline in this case, we're talking about the columns then are simply that new basis. Okay. That is the basis that we're changing into. That is the basis that represents T as the Jordan matrix instead of the standard basis. Okay. All right. So I hope you'll notice that the layout on the page here is extremely, I almost said similar, extremely analogous to what we wrote when we were talking about diagonalization. In fact, here's what we wrote. Flip back in the pages yourself if you'd like, but we wrote this for diagonalization. And the only difference is, what were the basis vectors? Here, it was a basis of eigenvectors. Right? That's what the story looks like when you diagonalize. You're doing a change of basis. You're conjugating. Of course, you're conjugating by a change of basis matrix, changing into a new basis script V. Representing T just in different languages. It's all the same, right? It's just that here, when you have a basis of eigenvectors, the result is diagonal form. And if you don't have a basis of eigenvectors, there's just not enough eigenvectors, well, you sadly don't get diagonal form, you get Jordan form. Okay. Almost diagonal. So close, just not quite. One little bit about terminology here. By the way, this basis, since this is the basis, this is a basis that allows you to get a matrix into Jordan form. I call it the Jordan basis, a Jordan basis. Weirdly, the book didn't give this a name that I was able to find. I think it's pretty important thing. It's something we're going to be referring to a lot, and so I'm going to make up this name. I think it's very reasonable. I'm going to call this a Jordan basis. Quick comment, it's not unique. Necessarily, probably not unique. So I should say a Jordan basis. Or you can say the Jordan basis if the implication is, the Jordan basis that we're using here. Right? But not unique. Okay. A quick reminder. You remember that whole business about, how do you remember where which one is the P and which one is P inverse? Exact same story here. Again, A represents T with respect to the standard basis. J represents the same T, just with respect to a different basis. So you're doing one of these change of basis conjugations, and then again, everything is kind of dictated by which bases are where. That's got to be the same as that. That's got to be the same as that, just like in the previous case. That's got to be the same as that. That's got to be the same as that. So right away, just thinking about what bases do you already know are being used for A and J, that tells you what the change of basis matrices are on either side that you're conjugated by. And then, look at whatever matrix, if you've been given P, if it is the change of basis matrix from V to S, we'll look for it in this list. Yeah. And it's wherever it shows up. If you've been given something different, maybe you've been given not P, maybe you've been given some matrix called Q. I don't know, that's the change of basis matrix from S to V instead. Well, then again, you can pick it out from this equation in where it shows up following this reasoning. Okay. Alrighty. Okay. So this next topic, you've already seen a little bit of this. There was a homework exercise that did something along these lines. I just want to flesh this out a little bit more detailed. Keep in mind, Jordan form is made up of blocks, right? We've got blocks inside of blocks. Here is a basic Jordan block. Here's another basic Jordan block. Here's another basic Jordan block, right? And you might ask, is there do they have to come in a certain order? What if I were to take these two blocks here and just, can I rearrange them? Is that okay? Does that matter? Does that still represent the same original linear transformation? Or what's going on there? So there's a nice realization to make, and that is that yes, you can rearrange blocks kind of however you want in a sense, just by reordering the basis vectors. So the basis, keep in mind if you're looking at a Jordan form, you're representing with respect to some basis. That basis consists of a bunch of vectors. Let's call them V1, V2, V3, V4, V5. I claim, I'm going to show you in just a moment, that if you want to rearrange the blocks, all you have to do is kind of rearrange the corresponding groups of basis vectors. So, for example, I assert here that if this basis gives you this Jordan form, then rearranging, so use that W basis now. Use the W basis instead of the script V basis. Notice all I've done with the W basis is it's still the same 5 vectors. Exact same 5 vectors. I just put them in a different order. And I claim this changing of the order shuffles the blocks accordingly. Like this. And we're going to walk through the details here. But these kinds of shuffling of the blocks, rearranging of the blocks can always be done by a rearrangement of a reordering of the basis vectors in the Jordan basis. Okay, so here's the details. Let's look at these blocks one at a time. Let's start with this block. That block corresponds to, you'll notice, the first two columns. What do the first two columns correspond to? The first two columns are telling me about the images of the first two basis vectors. So I'm going to say, roughly speaking, that this first block kind of corresponds to that first pair of basis vectors. Along those same lines, the second block, well, it's just in the third column. It's telling us about the image of the third basis vector. And then likewise, that last block, columns 4 and 5, basis vectors 4 and 5. Okay, so if you want to rearrange the blocks a certain way, just rearrange the basis vectors exactly the way the coloring would suggest. So notice here I'm putting what was the last block here. I seem to want to put that over here first. So what had been in the last two positions of the diagonal, you might say, because the basis vectors were the last two vectors in the list. If I want it first, just put those basis vectors first. I seem to be leaving this block right where it was. Third, still third. This block that was first, I'm putting it now sort of at the end. Put those basis vectors at the end. Whoops, missed. Okay, so I claim that's how this is going to work. Now, you may, oh yeah, go ahead. This is just an observation that you can. What we're going to find is that in some cases, it's not that we want to do it, it's that it's been done for us, right? And it's important that we make the realization of what does it mean if the blocks are rearranged. And the punchline is going to mean that it means nothing, and it's nothing to worry about. But we need to see why. In order to see why, we have to see that all block rearrangements can be achieved by reorderings of basis vectors. Yeah. Right. Okay, so now let me try to persuade you that this is in fact how this works. That specifically, if you think of this basis, that you get that matrix, but that if you rearrange the vectors, that you actually do get this as your matrix. There's some details to write down here. There's different points of view that you can take on it. I'm going to show you one point of view. Here we go. Let's think about, for example, what does this column here say? Where do we get that column from? And I remind you that if you're talking about a matrix representing a linear transformation with respect to some given bases, the columns tell you what the images of the input basis vectors are in the language of the output basis. So specifically then, what this column here says is this is the fifth column, so this is telling me about T of V5. It's the fifth column, so it's telling me about the fifth basis vector, the image of the fifth basis vector. And specifically, it's telling me that the coordinates of T of V5 are 1, V4, and then 6, V5. Is that a 6? I can't read my own. I highlighted. Yeah, 6. Okay, cool. 6, V5. Okay, so that column, this column right here is telling me this algebra. Yeah? I'm just going to now point out that, in fact, that exact same algebra is encoded in this other matrix. Here, let me get rid of that. Here, let's do that. Okay, so that column tells me that algebra. Now let's take a look at I guess I'll use red again. Let's take a look at this column. What does that column say? Now, it's a different column, right? So, is this telling me about the image of V2? Second column. No, slow down. This is the second column. Therefore, it's telling us about the image of the second input basis vector. Here, the input basis is script W. So this second column is telling me about the image of the second W vector. It's telling me about V5, just like the other one was. All right, so let's write that down. This is telling me, I guess I'll leave that highlighted. This is telling me T of V5. What is it telling me about T of V5? Well, it's telling me that the coordinates are 1 and 6 in the first and second vectors in that list, and therefore 1 times the first vector plus 6 times the second vector. And notice that's the exact same equation that was telling me. So you can take this one column at a time over all 5 columns of either one of these matrices, and what you will find is both of these matrices are telling you the exact same information about what T is. T does this to those input basis vectors, V1 through V5. So the matrices look different, but they're telling you the exact same information. Is everybody on board? Yes?
So in this example, you've moved the blocks.
Yeah.
Would it have worked if you completely scrambled the columns? That is, like, have you left column 1 the same and switched column 2 and column 1?
No. We have a very limited thing here. We're just shuffling blocks only. And the reason I want to shuffle just blocks is because I want to make a point coming up about different alternative versions of Jordan canonical forms, specifically about rearranging blocks. So I don't want to go off and explore other hypotheticals of different things we could do that don't pertain to that. Yeah. You're welcome to ask me in office hours, of course. Yeah. Okay. So does everybody see what's happened here? We have accomplished a rearrangement of the blocks by reordering the basis vectors, what I'll call accordingly. Okay. All right. Now I want you all to flesh out the rest of this example. There's 4 more columns. Interpret appropriately what each column says, and note that a different column in the second matrix, in fact, tells you the exact same thing. Here's a different way you could persuade yourself of this, by the way. You can just write down the change of basis matrix. Here, let me do this in a different color. Let me do this in green. You can write down that change of basis matrix. Right, I've got a big mess here. Let me get rid of all of this junk. Write down the change of basis matrix, keeping in mind that V is that and W is this. So you can totally write that formula for change of basis from V to W. What you'll find is it's made up of mostly zeros with a single 1 in every column. And if you write that down and conjugate this matrix, conjugate that matrix by this as your P, as it were, what you'll find is that you get as a result this matrix. And that's just a different point of view, different way to think about it. Gets you to the same conclusion. Okay. All right. So let me put a slightly different spin on this then. When you rearrange blocks, that rearrangement of blocks can be thought of as a change of basis. In fact, it's a special kind of change of basis. It's a change of basis that's really just a change of the ordering of the basis. Right? But it is a change of basis. Let me say that a little bit differently. When you rearrange blocks, like we see here, because you're just doing a change of basis, that means that rearranging the blocks results in matrices that are similar. They are literally similar. I don't mean that in the casual sense, right? They are conjugates of each other. So this gives us a nice result. This allows us, this allows us to state a nice result And that is, the punchline that I would like to get to is that every matrix has exactly one Jordan form. You can see why that's a nice conclusion, right? We already know that every matrix has exactly one reduced echelon form. It is, in a sense, true that every matrix has a unique diagonal form. And in a sense that we can make precise now, every matrix has exactly one Jordan form. Keep in mind, we're talking about by way of conjugation, by way of change of basis. So now here's the refinement I have to put on it then. Because all of these rearrangements, because all of our rearrangements are change of basis, what I have to recognize is that, technically the Jordan form isn't actually unique. This is one Jordan form for the matrix that we're talking about. This is another perfectly good Jordan form. Right? So if I were to just simply say, oversimplifying and say, Jordan form is unique, that's not true. Look at these matrices. These are different. Right? So Jordan form is not unique, but if I say, look, they're not unique. These are not the same, but they are similar. When you're talking about writing in Jordan form, you're talking about a similarity anyway. So if I were to say, up to rearrangements, ignoring rearrangements of the blocks, because of course they are similarities, then we have a substantial statement that's actually true. Ignoring rearrangements, every matrix can be put into exactly one Jordan form. Slightly different variation. Every matrix can be put into a Jordan form that you can then rearrange however you like, and however you like doing the rearrangements doesn't matter because those are also all similarities. Okay, so nice result. Here's a quick application. Let's look at these two matrices here. So we have eigenvalue blocks, basic Jordan blocks like that, whereas here we have basic Jordan blocks. Well, there's just the one basic Jordan block. The theorem that we just got through saying is that other than rearrangements, all matrices have exactly one Jordan form. Now let's look at these two Jordan forms here. These are not rearrangements of each other. Right? This is a really different Jordan block. There's no way to rearrange two small blocks to make one big block. You just can't do that. So by the theorem above, because up to rearrangements Jordan forms are unique, these two matrices cannot be similar. If the matrix you're dealing with, if this is its Jordan form, then this isn't. And vice versa. Okay. All right, so it's a little bit of a long story, but it's an important result. By the way, all the calculations that we did here are very very analogous to calculations that y'all are going to have to do in one of the homework exercises and in one of the AHPs, in that additional that PDF file that's linked. One of them is a question in 10 parts. And it pretty much is just about, what happens to Jordan form when you rearrange the basis vectors. Okay, so it'll be very much like this process that we just did. Alrighty. Okay, so let's talk about eigenvectors. Claim there's a relationship between Jordan form and eigenvectors. Let me point out very quickly why this is not surprising. Keep in mind where Jordan form comes from. Jordan form is our consolation prize as we were attempting to diagonalize. So we tried and failed to diagonalize, and we ended up, at least we have this Jordan form thing. Okay, how were we going to diagonalize? Eigenvectors, right? Eigenvectors were to be the basis that we were going to make up, right? So eigenvectors were in play as we were trying to diagonalize. The fact that we failed and ended up on Jordan form, but we were trying our best with eigenvectors. Right, so there's no surprise here that they're actually connected. Here's how that works. You can actually see it in the form itself. So don't forget, columns give you images of input basis vectors. Right? So one of these input basis vectors put into the linear transformation T, that's where your columns come from. Of course, don't forget, those are expressed in the language of the output basis. Right? Nevertheless, the columns are telling you, loosely speaking, about the images of the basis vectors. Okay. All right, so let's look at how that actually plays out for some specific columns. Now, let's suppose we have a basic Jordan block here. That's a basic Jordan block. Note the ones just above the diagonal. So not an eigenvalue block. This is a basic Jordan block, one of the small blocks. And let's pick some columns to talk about. Let's talk about the ith column, let's say. That being, let's say, the first column that hits this Jordan block. Okay. Well, that's the ith column, so it is telling us about the image of the ith basis vector. It's telling us T of VI. More specifically, though, it's telling us T of VI in terms of the V basis. Here, let me do it like this. It's telling us T of VI, but it's doing so in terms of the V basis, and so that lambda there in the ith position means that what that output vector is lambda times VI. That's straight out of section 5.3, just interpreting a column. A column tells you about the image of the corresponding input basis vector in the language of the output basis. Is everybody on board? Everybody with me so far? Hey, good news. That means we have an eigenvector. Right? T of VI is a multiple of VI. That means VI is an eigenvector. And let me just point out, this is not a rare circumstance, right? I mean, look at the structure of basic Jordan blocks. Basic Jordan blocks have a very simple structure. Lambda on the diagonal. One's just above. Every matrix of this sort has a first column. That first column will not ever have any ones in it because there's no positions just above the diagonal in that first column. The rule is that then furthermore, basic Jordan blocks have to be all zero below the diagonal. Therefore, there's going to be all zeros down here. And therefore, this is going to happen. This is always going to be the case. If you're looking at the column, the first column intersecting a given basic Jordan block, this is always going to be how it works out. Yeah? Okay, let's look at this other example then. Let's look at one of these other columns. Let's take this column, the jth column, not the first. Any other column that intersects with this basic Jordan block. Well, okay, it's not the first column. That means that the diagonal entry is not at the top. That means that there is a spot immediately above it, which of course, this being a basic Jordan block, that has to be 1. So I've got these coefficients of lambda on the diagonal, thus giving me that term. And then I've got this coefficient of 1 just above the diagonal. That gives me 1 times the previous Jordan basis vector. And so I get that. So T of Vj is Vj minus 1 plus lambda Vj. Again, that's straight out of 5.3. Just, the columns are telling us about the images of the basis vectors in the language of the output basis. Both of those bases being trivial. Okay. Everybody on board so far? By the way, that means that Vj is not an eigenvector. Right? If Vj were an eigenvector, I would need T of Vj to be just a multiple of Vj. That's it. But it isn't. It's got this other term in here pointing in a different direction, messing everything up. So, not an eigenvector. And again, this is always going to work out like this, right? If you're looking at a column that's not the very first one, then the diagonal entry is not in the top, which means there will be a 1 directly above it, which means there will be an extra term blowing it for being an eigenvector. All right. Okay, so in fact, here's another thing you can observe from this. Given a basic Jordan block, if you look at the corresponding basis vectors, the first one will be an eigenvector. The remaining will not. That's always going to work out. And so this allows us to draw a nice conclusion here. For every basic Jordan block, there is a corresponding eigenvector. You give me a basic Jordan block, I'm going to look at that basic Jordan block and say, hey, where's the first column? Hey, look what's in that first column. It's just a diagonal entry only. That's it. That basis vector must be an eigenvector, per the argument on the previous page. And furthermore, all the other basis vectors corresponding cannot be eigenvectors. So, grand total then, the number of eigenvectors, how many eigenvectors are there, given a Jordan canonical form? The number of eigenvectors has to equal to the number of basic Jordan blocks. Everybody on board? So, for example, let's look at this example here. Let's outline our let's outline our Jordan canonical form. There's an eigenvalue block. Let's look at that first eigenvalue block first. There are 2 basic Jordan blocks, and therefore this eigenvalue has 2 eigenvectors. Eigenvalue 4. There's an eigenvalue block for 4. 2 basic Jordan blocks, 2 eigenvectors. Does everybody see what happened there? By the way, I can tell you exactly which vectors are the eigenvectors. Furthermore, you can see it by where the blocks are. That first column has only diagonal entries. Therefore, V1, whatever the first basis vector is for this Jordan form, is an eigenvector. And then the third column has only diagonal entries, and therefore also V3. Everybody good? Okay. Alrighty. Just another example. Let's suppose that this is our Jordan form. Notice here there's only one eigenvalue block at all. Just a single eigenvalue block. The basic Jordan blocks are like this. Right? The first entries are the first one, telling us about the image of V1, and the third one, telling us about the image of V3. And notice, if I were to take this matrix, and just like I did back in section 5.3, if I were to take this matrix and write down what does that mean about these basis vectors, these columns with only diagonal entries are telling me these equations, which are telling me that these vectors are eigenvectors. Okay, same as on the previous page, more or less. How are we doing? Questions? Everybody happy? Okay. Right. Okay, so there's unfortunately, there's a bunch of stuff we just can't prove. It's just beyond what we have time for in Math 216. So I'm not going to prove that every matrix can be put into Jordan form. I'm not going to prove that up to rearrangements, every matrix can be put into exactly one Jordan form. It's just too much. We just don't have that kind of time. So that's too bad. Here's another thing we're not going to discuss. How do you find the basis? How do you find what I like to call the Jordan basis, or a Jordan basis? It's hard. So you're not responsible to know how to find a Jordan basis in general. In other words, if I just give you a raw matrix, here's an A, some random matrix, and ask you to find a Jordan basis. We're not going to talk about that. Now, nevertheless, sometimes, of course, you can. Every so often you get lucky. For example, if the matrix is diagonalizable, you do know how to diagonalize. Make a basis out of eigenvectors. Just find all the eigenvectors. Make a basis out of them. That's the basis that diagonalizes. And then just observe that when you diagonalize, what you've got is, in fact, a Jordan form. It's a Jordan form where all the Jordan blocks are one by one. Right? All these little trivial little Jordan blocks. So that is in fact a Jordan. You have Jordanized the matrix. So the basis of eigenvectors is your Jordan basis. Okay. Here's some. Every so often, you can also make certain other kinds of arguments. So, given a matrix A, y'all know how to find the characteristic polynomial. That's not that bad, right? So, a little bit of factoring, right off of there, you can immediately read a bunch of information. The fact that you have an eigenvalue of 1 with multiplicity 2, that immediately tells you about your first eigenvalue block. It tells you your first eigenvalue block is 2 by 2 with eigenvalue 1. And there's just only a couple of ways to do that, as it turns out, right? This is an example of a 2 by 2 eigenvalue block with eigenvalue 1. This is a different example, and those are all of them. So that's all there is. I mean, the process of elimination of sort of, we've already got it reduced down to a short list of possibilities. This other factor tells you about that you have an eigenvalue of 3 with multiplicity 1. That tells you that there is a 1 by 1 eigenvalue block down there. 1 by 1s are super easy. There is, of course, only one eigenvalue block. That's 1 by 1 with eigenvalue 3. So grand total, these are the only two possible Jordan forms. That's it. I haven't found the Jordan basis, but these are the only possible Jordan forms. So then how can you tell which is the right one? Well, another thing you do know how to do is to find eigenvectors. Go ahead and find your eigenvectors and then just see how many you get. So specifically, if for this first... let me do it like this. If the first eigenvalue, looking just at the first eigenvalue, if you have 2 eigenvectors, that would mean 2 basic Jordan blocks, and that means this is your Jordan form. Other possibility, maybe there's only one eigenvector. Again, you all know how to find eigenvectors. If there is only one eigenvector, that means there is only one basic Jordan block. And then this would have to be your Jordan form. So, like I say, sometimes you can figure out the Jordan form even if you don't have the Jordan basis. Okay. Lastly, real quick, and let's see, we have a minute and a half. I'm going to mostly let y'all read this, but a quick observation to make about how to enumerate possible Jordan forms, sort of harder than what we just did, is just think about how many factors you have here. So if you have a multiplicity of 4, what that's telling you right there is that you have a 4 by 4 eigenvalue block, and there's only so many ways to make basic Jordan blocks inside of there. So, for example, you could have a single 4 by 4 basic Jordan block, which would look like that. Or you might have a 3 by 3 and a 1 by 1. Or you might have a 2 by 2 and a 2 by 2. Right, so you can enumerate a bunch of different possible forms. The nice thing about it is it's very easy to write down, just kind of just slowly and carefully, all the different ways that you can have positive integers add up to 4. Each one of those corresponds to a basic Jordan block structure, and you can therefore count how many possible basic Jordan block arrangements you might have. So, details for you guys to read on your own. See you later. Have a good Wednesday.